Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Joining us today on Superheroes of Science, we are so pleased to welcome Professor Tim Donohue from the University of Wisconsin-Madison. So welcome.
Thank you, Sarah. It's great to be here. It's an honor to talk to you and your audience about some of the things that we're doing at the University of Wisconsin to create a green, low-carbon future with biomass. So before I get into the nitty-gritty of what that really means, I thought I would tell you a little bit about myself and what I do for a living here at the University of Wisconsin. As the slide shows, I'm a professor in the bacteriology department. That means I was trained as a microbiologist, but I like to refer to myself as a green, renewable energy microbiologist that's different than the people who study microbial pathogens that have kept us locked up in bubbles and wearing masks for the last 18 months. But we're all important. In addition to being a faculty member in the bacteriology department, I have the pleasure of directing something called the Wisconsin Energy Institute. And this is the picture of the building here on the right. This is a collaborative home for energy research and training at the University of Wisconsin-Madison. It houses a diverse set of multidisciplinary research teams working on everything from new electrical grid technology, how we power cities and homes. What I'm going to really focus on today is work that's going on in something called the Great Lakes Bioenergy Research Center that I also have the pleasure of directing. This is one of 4 bioenergy research centers established by the U.S. Department of Energy in 2007. And the goal of each of those centers is to develop sustainable fuels and chemicals from something that I'll define in a minute called energy crops grown on land that is not used for food production. And in that center are some 475 students, staff, and scientists. So it's a broad interdisciplinary center with people here at Wisconsin and actually 5 other institutions in the US and Canada. So let me now shift gears and say a few words about bioenergy, and let me answer the question of why would anyone want to think about bio-based energy solutions? And the first reason is on the next slide. I want to point out that we and a lot of other people believe there's a need to diversify how we generate and produce energy for society. Diversification is essential to energy security, and I'm going to illustrate that with a couple of things that I've stolen from the web here. On the bottom left here is the track taken by Hurricane Harvey in 2017. And you can see it came in from the Gulf, went up through Corpus Christi, made a U-turn and went back and over the Gulf and then impacted Houston, New Orleans, and the whole Midwest, taking down fuel production and chemical production in the Gulf of Mexico for months. So that created an insecure situation. Lest you think that that's a historical accident, last week I had the unfortunate pleasure of downloading similar highlights about the effects of Hurricane Ida that just hit the Gulf and went all the way through the Midwest and up to the East Coast, and actually had as large of an impact in New Jersey and the Northeast as it did in the Gulf. But the bottom line is that also took down power and industrial activity in a large fraction of the United States. So those systems are insecure to natural disaster. A way to stratify or make them more resilient is to have backup systems, for example, bioenergy, that we could leverage when the traditional fossil fuel-based energy systems go down. The other reason to think about bioenergy is to address something that I'm going to spend a few minutes talking about now, and that's greenhouse gas emissions. So what are greenhouse gases? So to explain what greenhouse gases are, on the left here, I want you to remember that the sun is out there and warms us up by solar radiation, and the planet Earth acts as a mirror in many cases because it takes that solar radiation, uses it to warm us, but reflects some of it back out into the atmosphere. This is this re-radiated heat. For hundreds and hundreds of years, that heat has been dissipated or taken out into space, and we don't feel it on the planet Earth. But more and more, as greenhouse gases have been collecting in the atmosphere, that radiated heat cannot get out into space. You can think of these greenhouse gases as the equivalent of insulation in your house. The heat comes in, and instead of going out to the atmosphere, your thermal windows and the insulation in the house keep it in, so you don't need that much energy. Well, the more and more greenhouse gases that have been collecting in the outer atmosphere of the Earth, the more and more that heat is not escaping to the atmosphere. So scientists believe that these greenhouse gases are a major cause for the increased temperature on the planet, as well as other things, including, more extreme weather events like Ida and Hurricane Harvey that I just talked about. So where are these greenhouse gases, CO2, carbon dioxide, methane, CH4, or N2O, nitrous oxide, coming from, and how big of a problem are each of those? So over here on the right is an overview of the amount of greenhouse gases in the US in 2019. And most of that is carbon dioxide, small fractions of methane and nitrous oxide, and some fluorinated gases that industry produces. So the large one is CO2 or carbon dioxide. That creates a problem. But methane and nitrous oxide, even though they're only a small fraction, actually create a larger problem because they sit in the upper atmosphere longer than CO2. So once they get there, they're there for hundreds or thousands of years, whereas CO2 is slowly released into the atmosphere, or in a minute, we'll talk about how it comes back into the planet, okay?
Where does the nitrous oxides come from? I mean, CO2, it's kind of, we know it's primarily burning of fossil fuels, but the nitrous oxide, I had not, where does that come from?
CO2 comes from us breathing in a process called respiration, as well as from burning fossil fuels. Nitrous oxide, over 80% of it comes from farming.
Oh.
So when most farmers grow crops for food, they need to add fertilizer, that's ammonia, and there are bacteria in the soil that can convert excess ammonia that's not used by the plant into nitrous oxide, and then that dissipates out into the atmosphere. So most of that nitrous oxide comes from farming. Okay. Industrial production agriculture, okay? So you just teed me up, Steve, by asking me about where that CO2 comes from. Although I said we breed some of it, human and animal activity is a source of a small fraction. Most of it comes from using fossil fuels. Over half of it, almost half of it, comes from petroleum, with the major parts of the rest of it coming from burning natural gas or burning coal. Okay? So what do we use petroleum for? The next slide shows you that petroleum is something that we have become dependent upon. President Bush once said we were addicted to it in 1986 in his State of the Union address for fuels and chemicals. That includes fuels for cars, diesel engines like shipping and naval, and jet fuel. And it includes thousands of products that we depend on: lubricants, plastics, clothing, and even some medicines or drugs that we depend on every year. In the US, the petroleum industry is itself a multi-trillion-dollar a year industry. If you look over here at this barrel of petroleum that I've sliced up to illustrate a point, about half of this value from the petroleum comes from fuels in gasoline, diesel, and jet fuel. That represents about 3/4 of the volume. The other half of the value comes from a small fraction of the volume, but it represents tens of thousands of chemicals that we as society have grown to be dependent upon.
Wow.
Plastic wrappers, clothing, et cetera, carpet, window shades, you name it. We as consumers look at the price of a gallon of gas every day as we drive into work or drive home. And we say, oh my God, the price of gas is going up, the price of gas is going up. Fuels are the high volume, low profit material from a barrel of petroleum. Chemicals are the low volume, high profit materials. And it's the money that the petroleum industry makes from selling chemicals that allows them to keep the cost of fuel as low as it is today. We may not think it's low, but if it wasn't for chemicals, it would the price of fuel would be even higher. And that's the point I'm gonna come back to when I start talking about the strategy that we're using to reduce our addiction to petroleum and begin to think about biomass as a source of the fuels and chemicals that we currently get from a barrel. Okay? So now let me shift gears and say, what if we could make these same fuels and chemicals from plants that remove CO2 from the atmosphere to help remove that greenhouse gas layer, instead of fossil fuels, which when burned are adding net CO2 to the atmosphere. So what we're working on in Great Lakes Bioenergy is harnessing the power of plants to utilize sunlight and capture CO2 in a process called photosynthesis and use that plant material, biomass, as a source of fuels and chemicals. So that would be great for a variety of reasons. Let me come back and first show you how important this would be in helping us deal with the greenhouse gas emission situation that I started with. So on this next slide, scientists, this IPCC group, which won the Nobel Prize for predicting and challenging us to think about greenhouse gases, has said to limit global warming, we will need great changes in agriculture. Zero carbon farming, which means no carbon inputs into the ground. Carbon and nitrogen sequestration, that means capturing as much of the carbon as we can into the above ground part of a plant, but also into the roots. So it's buried in the ground and not released into the atmosphere. In crop activities, in forestry, and in grazing, animal grazing activities as well. So that's why this over here is called AFOLU for agriculture, forestry, and other land use. If we grow crops a different way than we do now, we should be able to use less fertilizer, and less fertilizer could mean less nitrous oxide going into the atmosphere to contribute to greenhouse gases. And this is a process that the experts called bioenergy with carbon capture and storage. The storage is capturing and keeping carbon under the ground. So instead of having short, simple root systems, having deep, complex root systems that keep the carbon under the ground. And if successful, the estimates are that we could remove 100 to 1,000 gigatons of CO2 per year by the 22nd century. That's half of what this group called for to reduce global warming and help us mitigate the effects of climate change. Okay? So this is why. Now let me make believe I'm teaching a bioenergy class and go into bioenergy 101. What can we use to make from this plant biomass? So the potential uses of it are power, electricity, heat, and that currently is 65% of the energy sector in the United States. The other major uses of it are transportation fuels, ethanol for cars, hydrocarbons, gasoline for cars, diesel for jets, diesel for shipping, and naval. And that's about a third of the US total. If I was giving this as a public lecture with a larger real live audience than Steve and Sarah, I would typically give people a quiz and say, not give them the numbers up front and ask them what fraction of the total energy use do you think is in the transportation and power sector, and most people get it wrong. They think most of what we use is for transportation. They forget that we live in a world where we require a lot of heat, we require air conditioning, we have become so accustomed to those things, and we don't see them when we drive into work every day, that they become silent or invisible to us on a daily basis. And again, the other uses for bioenergy 101 are all those industry and consumer products that represented the 15% of the barrel that I talked about. Plastics, fertilizers itself, medicinals, and industrial chemicals, okay? And so again, why bioenergy? If it's done right, and I think done right in quotes is the important part, it can fuel a green bioeconomy. It would allow us to lower greenhouse gases. It would allow us to use all of these abundant raw materials that we currently produce every year in the United States and around the world. And instead of throwing them away or burning them and releasing CO2 into the atmosphere, convert them into chemicals, materials, and fuels that we currently derive from fossil fuels. So therefore, it would reduce our reliance on petroleum and diversify sources of cost-competitive energy and chemicals in the United States and elsewhere around the world. And that's really the final point here, is that it allows regions of the planet and the country to have whole new economic sectors based on what's available to them on the left part of this cartoon to create jobs and economic opportunity. It expands energy justice to parts of the country and parts of the world that have not traditionally benefited from the production of petroleum or its conversion into fuels and products. So you may say, well, this is all great, when is this going to happen, and why haven't we been doing this? Well, my next slide shows that biofuels and bioenergy is not a new idea that Tim cooked up in the year 2100. Over here on the left is an article I stole from the web from the New York Times in 1925. I'm not old enough to have subscribed to that paper then, but I found this on the web. And it talks about a gentleman by the name of Henry Ford, who had just built the first automotive plant that was going to build cars on an assembly line. And he knew how to build them, but he didn't know how to fuel them. And he didn't know how to make the gasoline to run all the cars the Ford Motor industry was going to build. And in this article, he says the fuels is going to come from fruit like the waste on the road. He called it the stomach out on the road, from apples, weeds, sawdust, any vegetable matter that can be fermented and left over from people eating. And here's a picture of a gas station in Lincoln, Nebraska, another Big Ten town, in 1933, with a gentleman in a nice white garb pumping corn alcohol blended gasoline with the same amount of alcohol in it that we currently add to gasoline today, 10%. So this is not a new idea. Why is it that Henry's vision in 1925 was not captured in the gasoline that this gentleman was putting in the car? It was only 10%. The reason it wasn't is because companies like Sun Oil of Ohio and others in Pennsylvania had discovered oil and began to pump it to make lubricants and oil to burn in people's houses. And they really realized they had an extra amount of oil that was too heavy to burn and didn't have a use for it. So in the original days, they were throwing it into Lake Erie and the rivers and creating pollution problems. And Henry met the Rockefellers and the owners of the oil companies, and the rest is history, because now we have an industry that uses oil, hydrocarbons, to power those cars, power your diesel engines, and power your gasoline. But we still want to get to a different place that Henry wanted us to get to, and that is to use biomass as a source of some of these fuels and chemicals. Now what I'm going to do is tell you what we're doing in Great Lakes Bioenergy to help us get there. So we're using so-called non-fuel, non-food energy crop to make the same compounds that we can get from a barrel of oil. And this non-food energy crop has got a technical term called lignocellulose, and the U.S. Department of Agriculture and the U.S. Department of Energy estimate that there's over 1 billion tons of that produced on the land in the U.S. every year that is not used for anything industrially. And if we could figure out how to make these same compounds from lignocellulose, it could replace 30% of the fuels and chemicals without having a negative impact on food production. Even if we're successful at this mission, we're only going to replace 1 out of every 3 barrels. There's not enough of this to replace all of it. People want me to say we're going to do that, but there's just not enough of it produced on the land, given how much we use. The benefits of that is this technology would have a 3 to 5-fold lower carbon footprint compared to burning fossil fuels and making chemicals from fossil fuels. And it has the potential to build new local fuel and chemical industries all over the United States and the world if we develop it. So again, why lignocellulose and why and what are these? So again, I already said this, we produce over 1 billion tons of this every year. We are not talking about corn. We are talking about woody biomass like poplar that take 3 or 5 years to grow and harvest, switchgrass, perennials, or energy sorghum that we grow to produce energy. These are non-food crops. And in a minute, I'm going to show you that we can produce a lot of these on non-food land. So let me go to that now and illustrate that with a map of the north central region of the United States. This is a part of the country. When I grew up in New York City, it was kind of foreign to me. It was always referred to as the breadbasket of the US. And this map shows that. It shows the land from Ohio to the Dakotas and Nebraska. And the light counties are all the counties that are used to grow crops for food. And they're light because their productivity in tons of biomass that are produced every year is low. But it's valuable productivity because it grows corn and soybean and wheat that we and animals need. The dark green counties are counties that are not suitable to grow food, but are perfectly suitable to grow energy crops. And you'll see they are dark green because their productivity outstrips the food land. There's a lot of those counties and a lot of that acreage. These circles are places where we have modeled there's enough biomass to produce locally and ship it to a refinery in the middle of that circle that would make fuels and chemicals. So there's 35 of those in the upper Midwest, and there's even one over here pretty close to the Purdue campus, I think. And there's a couple over here in Wisconsin, and a couple in Michigan at our partner institution in East Lansing. So these would be energy crops grown on non-agricultural land to produce fuels and chemicals that we currently get from petroleum. This middle graph is another view of the same acreage where I've now gone in and looked at the land where we produce fuels and colorized it a different way. And this color scheme, it's hard to see. It's based on us looking at the productivity of 9 million acres of land that are used to grow food over the last decade and segregating them into green fields, red fields, and blue fields. Blue fields and red fields are ones that our agricultural experts say are of a productivity so low that a farmer is not making any money on it by growing crops for food. They're only making money on the green parts of that acreage. But they continue to farm it that way because that's the way their grandparents and their parents have been farming it. And they continue to put fertilizer on that ground and pesticide, and that creates nitrous oxide and greenhouse gases, okay? So we think there's subfields or plots within that agricultural acreage that could actually be flipped to grow bioenergy crops. And it's about 20% of that total acreage, but it's not enough to make it so that I can't buy corn when I go to the farmer's market this weekend. And it's not enough to prevent animals from having animal feed. It shouldn't interfere with food production. So we've been modeling all of this, the climate, the ecosystem, and the economic benefits. Again, going back to this green barrel idea of making fuels and chemicals from biomass. Okay, so we work with a lot of agronomists and modelers and field scientists to look at these acreage, but we also take things from that information and we bring them into the lab and we try to figure out what we're going to do with this biomass to make fuels and chemicals. So what does it really mean to make fuels and chemicals from dedicated non-food energy crops? Well, I want to compare what we need to do over here in a minute with what we currently do now. That gentleman in 1933 was pumping ethanol blended gasoline into a car that came from corn kernels or corn starch. And that's a simple process that they could generate in 1933, and we still do it now. That's where the 10% of the ethanol in our gasoline comes from. If you lived in Brazil, you wouldn't be making ethanol from cornstarch, you'd be making it from sugarcane. A simple process that ultimately gives you a single sugar glucose that can be fermented into ethanol. Many of you or your parents, if I have a school age audience, have also experienced this fermentation into ethanol because that's what we do when we make beer or wine. It's very simple. It can be done for a lot of industrial uses. This is very different than what we're working on in Great Lakes Bioenergy to make tomorrow's lignocellulose products. We're going to start out with lignocellulosic biomass. So to put that in real terms, some of you are probably wearing a cotton shirt or a cotton pair of pants. And you are, if you are, you're wearing lignocellulose. And you know that that's tough material because when you or your parents put that in the washing machine, it comes back out. It doesn't dissolve. And it comes back out even if you put bleach in it, or if a caustic chemical, or you run it at high temperatures. So we have to develop new ways of treating the biomass to get it to dissolve, to produce the materials that we can generate, that we can use to make hydrocarbons and chemicals. And a lot of the processes that we need to use microbes to make hydrocarbons and chemicals are not necessarily processes that these bacteria and yeast have been using for millions of years on the planet where they're normally found. So we're actually generating designer microbes where we steal genes and enzymes and put them together into industrially ready organisms that we can use to make these compounds from the sugars in the cellulose and the phenol, the aromatic compounds in the lignin, okay? So what are we talking about when we're talking about hydrocarbon fuels? We're not making ethanol. We're making compounds that are longer chain alcohols like isobutanol or these other molecules here that are chemically mimics or equivalents of what the petroleum industry gets out of a barrel of oil. And that's an advantage to us because we're able to mix them at 10%, 20%, 30% with fossil fuel hydrocarbons and burn them in the same engines that Ford, GM, Toyota, aviation engines are already used. You will not have to buy a new car or put a new engine in your existing car to use these fuels.
Now, is this still in the works, or do they actually have these now?
We're pretty good at making this compound and these compounds at university scale, not at 30 millions a gallon per year. We don't do that at universities. We need to work with industries, and we work with a lot of them when we make these advancements to patent them, and then they license them and they see if they're going to scale them up. Over here is a picture of an organism that we work on in the center, a bacterium that we have figured out by a single gene change to get them to secrete this type of a molecule into the media and overproduce it, so that industry could take these lipid droplets out of the media and burn them directly. This is kind of like taking a bacterial fermentation and turning it into a salad dressing bottle. So if you go in your refrigerator tonight and you have a bottle of oil and vinegar in the refrigerator or even on the shelf, you'll see the vinegar, the water part is at the bottom and the oil is at the top. So this bacterium, when it overproduces these lipid droplets, you can actually, in theory, skim them off the top of the aqueous solution, and with a minimal amount of processing, which means a minimal cost to industry, you think about burning them in an engine as a fuel molecule. Okay? The other types of things that we're making, I'm not going to get into the chemistry, are plastics that come from either the sugar component or the lignin, which is an aromatic component, industrial chemicals, that nylon, again, maybe some of you are wearing polyester. That's not one of my favorite things, but you might be wearing a quick dry shirt that has, you know, polyester fabric in it, lubricants for oils in the house or in your car, natural fertilizers that are green. They don't come from petroleum. Medicinals, I'm going to come back to this one. Many of you have probably taken or been given acetaminophen is the chemical name, or Tylenol. If you have an inflammation from running or exercising. Acetaminophen is the active ingredient in that anti-inflammatory treatment. That comes from coal tar. We can now make that from biomass. We have a patented technology to make acetaminophen in 2 steps that are green. When that first came out, we patented it. It went all over the web as green Tylenol. We didn't want to advertise for one drug company, but again, there's a lot of things on this slide that you don't think about every day that come from petroleum that we are working aggressively to make from the chemistry in biomass directly. So I've tried to give you some high-level examples of what we're trying to do. We're trying to optimize the low-carbon production of valuable biomass on non-food lands. That's looking at sustainable cropping systems. By low carbon, I mean low amounts of fertilizer, low amounts of pesticide, and deep roots. Fertilizer, in addition to being a source of nitrous oxide, is made by a process called the Haber-Bosch process. And that's Haber-Bosch uses 1% of the United States energy every year just to make fertilizer. So if we can grow crops that require less fertilizer, we can cut down on the carbon input into agriculture. We're trying to make products out of as much of the biomass as possible, sugars to make fuels, hydrocarbons, bioproducts from the lignin, the aromatics. I gave you one example of actually Tylenol or acetaminophen. The organic fertilizer is actually something that's a product that comes from lignin. And although we're academics, we do a lot with agronomists and refinery builders at an academic level to model how this is going to work when it's deployed by industry. That's how we came up with those models of 35 circles in the Midwest and where you could place them. Industry does not want to haul biomass 1,000 miles to a refinery to make it into fuels and chemicals, because the transportation costs will kill you. That's why every one of those refineries is in the middle of a circle that has a radius of no more than 50 miles, so that the transportation cost is low and that community can benefit from what they grew. And again, by doing that, we have a vision that we will be producing value for biomass producers. Those are called farmers. The refineries that will grow in the middle of those circles, the consumers that will be able to buy locally sourced fuels and chemicals, and the communities that house that activities. Many times when I give talks to local groups, they want to know, what does success look like? And I will often say, success looks like you driving your car to a Rose Bowl game, and you can pick your favorite team, using fuels that were grown in Wisconsin or in Indiana, or to a Super Bowl game to see the Packers, or maybe even this year, a World Series to watch the Brewers, right? Not the Cubs, but or the Yankees. I'm a Yankee fan. Okay. So again, down the road, in my view of the world, the green landscape will be diverse. It'll have energy crops feeding a biorefinery. It'll have wind farms. It'll have solar panels, and it'll have hydro-produced energy, so that it'll be diverse and more resilient to natural or man-made events that threaten that. But this future needs new superheroes. So these are the young people that are out there that are really going to make a difference. And I hope you see something here today that you want to at least consider as a career when you choose your academic and future career path. This industry will require everything from truck drivers to move that biomass, to scientists working in those refineries, to policy people and IP people creating the instruments that allow the vision that these lab people create to really be deployed in the field. For those of you that are teachers, I want to leave you with this website and the idea that you and your students can look at some units that we've developed in Great Lakes Bioenergy that allow you to do side-by-side comparisons on biofuels and fossil fuels. Look at some of the technology to convert cellulosic biomass into ethanol. We have an ethanol in the bag experiment that we do with students here all the time. We used to do them in person when we were allowed to, but with COVID, we haven't done them that often. We're looking forward to doing them again. But you can do this in your classroom with biomass you can pick up at the supermarket, or if you're close to a cornfield or a soybean field, or have weeds growing in your backyard like I do, you can do it that way as well. And then there are other examples that allows you and your students to use household items to see where the majority of the Earth's carbon is located and how it moves through the ecosystem to become greenhouse gases, and what you could do to change the equation now. So with that, I'm gonna stop.
Thank you for listening to this episode of Science from the Experts from Purdue University Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.